Assalamu alaikum students. I welcome you all to our new lecture on hydrology and water resources management. We are reaching almost to the end of our course contents. We went through the runoff and hydrographs in the last lecture. We went through unit hydrographs and the way how to calculate the unit hydrographs. So we went through those things in the previous lectures. At the end of this course contents, we are going to look into stream flow routing, introduction to floods, and its causes. So basically these 2 or 3 lectures are covering floods and routing. These are very important concepts that you should understand, and you should be able to apply the concepts ultimately in the practical field. These are as usual the references that we are using for the content. The main book is the first one, Venti Chow, Applied Hydrology. This is already shared with you. Some sections of it or relevant sections are already shared with you through LMS. You can also contact our librarian who can give you, or he can provide you the PDF of this book. So it's very important that you go through the contents in the book as well. So these are the contents that we are going to follow: introduction to floods and its causes, frequency and duration analysis. For this we will be using some Excel exercises, and then the most important are the reservoir and the channel routing. These are the things that we will be trying to cover today, or in this lecture at least. And then we will be left with flood control structures and introduction to hydrological modeling, another very important part of hydrology. So let's continue with the introduction to floods. You see, you would have observed or you would have observed, in at least in the news, about the floods that are occurring in Pakistan. This is basically one graph that is in front of you from World Resources Institute, and they have kind of estimated the expected population that is affected by river floods in millions. So you see, all the top countries which have the most people affected by the floods are either developing countries or are the countries which are, let's say, at the very lower ladder in terms of economy. India, Bangladesh, China, I mean the number of population that is exposed to flooding is huge. Pakistan is somewhere here. 0.71 million people are exposed to floodings every year. The effect of floods in terms of economy is also very significant. You see here again, these are the numbers from the same source, which gives us an idea the percentage of economy, or let's say the absolute values of GDP that is affected by the river floods. On the right hand side, these yellow bars show you the estimated GDP that is affected by the flooding, and on the left hand side are the absolute values in millions of dollars. So for example, if we are looking at Pakistan, it is showing something $1,732 million are lost due to flooding in Pakistan, which is almost 1% of the GDP. So you see, quite a lot of money is lost because of the flooding, or the destruction that is caused by flooding. Also, the expected population in terms of the flooding in 2030, it's a very big number. If you add to it the climate change effects, I mean, we are basically a country which is fed by Indus River, and Indus River is basically coming from the glacial melt, and glacial melt is something which is mostly affected by the climate change. So it's understandable that we are also going to be affected quite badly by the climate change in the times that are coming. So these are the numbers in terms of population, in terms of the losses due to the climate change. So in all aspects, whether it's population, whether it's economy, or whether it's because of the climate change in the coming years, we should be concerned about the floods and its effects. We have gone through basically all the basic information that is required in hydrology. We have gone through all the important parameters and the precipitation, stream flows, unit hydrographs, all those kind of things. Flood, if you look at hydrograph and if you associate it with the precipitation that is occurring, so let's say, for example, if this is a rainfall with different values in terms of millimeters or inches, and then this is the hydrograph at a certain location in the river, then you would always see that there is certain lag time between the maximum of rainfall that has occurred and the maximum of discharge that is occurring. So there would always be certain lag time that would be there. So the flood peak would be occurring in terms of 2 days or 3 days after the maximum precipitation is occurred. Obviously this would depend, this x-axis would depend upon where we are, where are we recording the hydrograph. It can be in hours, it can be in few hours, or it can be in days, depending upon where we are. For example, if you are recording a hydrograph at Sakkar Barrage, and you are trying to find out what is the effect of increase in discharge because of precipitation somewhere in the northern areas, then obviously that peak would be showing down in the Sakkar Barrage somewhere in 2 to 3 days. If you are looking at, let's say, Nowshera, or you're looking at the Atak Bridge, and you are trying to find out the effect of precipitation on the flood, then that would be instead of 2 to 3 days, it would be a 1 day or something like this, depending upon where the precipitation is occurring. So this lag time is an important indicator where we can plan, we can manage, and we can prepare ourselves for the upcoming flooding situation. Again, this is more or less the same diagram, but we just want to look at the rainfall events and then the peak of the discharge. So here in terms of days, you can see that precipitation is occurring on, let's say, around in the evening time of day 1, and then somewhere in the mid day on the second day you have the peak of discharge. Most of the things here that are shown are already covered in the previous lecture, so I'm not going to go into the details of these things. The base flow is known. There was one question from one student which I answered was, why is the need of dividing the base flow from the hydrograph? And basically the need is because we want to know what is the effect of this precipitation on the discharge. This part of the hydrograph is that part which would always be there in the river. This is the water that is flowing in the river always, whether there is precipitation is occurring or not occurring. But then we are interested that if there is certain amount of precipitation occurring, then what is effect of this precipitation in terms of the flood peak? How much additional water is it bringing in the stream? Because if we know the additional water, the amount of additional water that is coming into the stream, we would be able to plan ahead in terms of time and in terms of resources that are available to us. Fine. Now that you know the complete hydrological cycle, you should be able to say something about the factors which would be affecting the flooding. The important variables are obviously, the most important is the precipitation. How much precipitation is occurring? What is the area like where the precipitation is occurring, where there is excuse me, If the slope is very steep, if the slope is steep, then obviously all the precipitation that is occurring, or most of the precipitation that is occurring, would have very little time for infiltration. It will come to the stream very quickly, resulting in discharge. Similarly, the land use, whether it's the land is used for vegetation or whether it's a barren land, all these factors would be very important when we are looking at the floodway, or at the flood wave that is coming in the river. And then these flood waves or these discharge would be shown with the help of different kinds of graphs. These graphs might be yearly water year. So water year is not from January or December, but it is, for example, depending upon which country we are looking at, it can be from the June, July period to the next June period. So this would be a water year, and for that particular water we would be looking at the discharge that is occurring every year in a particular level. Discharge would be either in Q6 or Qmix, depending upon what values we are using. Then there can be the discharge can also be shown in terms of the calendar years. What is the maximum value that is occurring in a particular year at a certain location. So for example, here we are looking in terms of, not in terms of the discharge, but in terms of height, that what was the height in 1951, the maximum height at certain location of the flood wave, 2 meters or 4 meters or other values. So different kinds of graphs would be there, but the ultimate important thing is that we have a kind of relationship between discharge and stage. Stage, as I said earlier, is the depth of water. So if we have, for example, let's say for the last 20 years, we have the record where we say that the maximum discharge when occurred had this depth, then we can kind of plot all these values and we can put an average line through that data, which is usually called the fitting of data. This is something that you would be learning in other lectures, but we kind of draw an average line which represent all the data set here, and then we have kind of a permanent relationship that we can use in future coming, let's say 10 or 20 years. And floods in Pakistan are a recurring phenomena. You would still remember the 2010 flood, the super flood that occurred in Pakistan. And this is just a comparison of the two satellite pictures of the same location, August 2009 and then August 2010. This is the normal Indus River flowing. You can hardly see the river here. It's such a thin line, and then in 2010 you can see what the difference is between the two pictures. And this basically, you would see here this discontinuity, and this is because of the Sakkar barrage. So Sakkar barrage was successful in warding off the maximum discharge, and due to that we kind of spared ourselves from a lot of damages. Anyways, the effects of floods on the human side is huge, whether it's shelter, whether it's economy, disturbance in livelihood, or destruction of property. So the effects are quite huge. What we usually look into, the parameters that are important for flooding, are usually this Q100 and Q500. And Q100 would be the 100-year flood, and Q500 would be a 500-year flood. Now, Q100, or let's say 100-year flood, does not mean that this flood is coming just once in 100 years. It can be more than that, but it just tells us the return period of that, the approximate return period of that amount of discharge. So we usually have these numbers, and we try to plan, or we try to manage our resources, our structures for these kind of floods. So for example, let's say we are looking at 100-year flood, and the 100-year flood has a maximum flow depth of 1.84 meters and a maximum velocity of 3.29 meters per second. The volume is something like this, in 1000 of cubic meters, and the area that it would inundate, or the area that would be affected by a 100-year flood, would be this much in thousands of square meters. Obviously, when we go to the higher values, or to the 500-year flood, then these values would be larger than this one. So we kind of estimate these values, and those values are then used for planning purposes. Now, it's important to understand the types of floods that are occurring. Usually, we can divide roughly different kinds of flood in riverine flooding, urban drainage, ground failures. Because of ground failures, there are floodings, fluctuating lake levels. The normal lake levels, they usually would fluctuate. If there are, let's say, disturbances in the upstream areas, then the lake levels would fluctuate. And basically we usually define the surface runoff as, or the flood situation as, when runoff or rainfall is more than the infiltration capacity of the soil, and it also exceeds the evaporation rate. So water is coming down, less water is going up in terms of evaporation, less water is infiltrating into the soil because of, let's say, the intensity of rainfall. And if these situations are there, then the flooding situation would be there. Also, it depends upon what kind of surfaces this precipitation is falling on. We already looked into these things, so I'm not going into the details, but if we are in the urban area and most of the area is covered or impervious, then all the precipitation that is falling would ultimately turn or change into surface water runoff. There wouldn't be any kind of infiltration there. So in urban areas, we would be having very quick response of precipitation in terms of flooding. In agriculture areas or land use where there is enough time for water to infiltrate, there would be more time for the surface runoff to occur. And across the surfaces, there would also be difference. I mean, either it can be confined flow, when there is a certain kind of boundary within which the water is flowing, if we are looking at unconfined flow, then unconfined flow basically means where your flow is very broad. It's a kind of broad sheet of flow, and it can also bring with itself a lot of contaminants or a lot of debris or a lot of other things when it is flowing. Riverine flooding is basically the flood which is occurring into the streams, when basically there is less capacity of the stream, or let's say there is more water coming into the stream more than the capacity of the stream, then the flood resulting from that kind of situation is called riverine flooding. And its dynamics are also very different depending upon what kind of terrain we are looking at. If the terrain, or let's say the area, is flat area, then the riverine flooding is usually having a very shallow depth, and the velocity is also slow. It has low velocities, slower depths, or smaller depths, and it stays there in the area for a longer period of times. It can be days or weeks, depending upon how large the flood is, because the area is flat, so the drainage wouldn't be that effective, or let's say very efficient, so the water would stay for a longer period of times. If the area is hilly area, then the depth would be larger, the velocity would also be higher, and the time for which that flood would stay in that particular area would be less. Yeah, because we have hilly area, the slopes are greater, and the water flows very quickly out of that area. So these are basically the riverine flooding. Riverine flooding basically means when your channel or your stream or your canal has less capacity to accommodate the flow, and the water overflows the stream banks. Another type of riverine flooding is the overbank flooding. Again, when the water, usually it occurs in the rivers and streams, and this again is a larger volume of water coming into the river channel and then bursting out of its embankments and flowing into the adjacent floodplains. So you would always have some kind of floodplain area around your river. Overbank flooding would be that kind of flooding where the river is exceeded by the incoming flood and it infiltrates or it goes into the floodplain area that is being designated for flooding. Flash floods usually occur in the hilly areas. There is a certain time which is usually associated with it, which is 6 hours, that if, let's say, a kind of event has occurred, the causative event, it can be a rainfall event or maybe a dam failure, but whatever the event is, if the reaction of that event is shown in shape of flood within 6 hours of time, then usually we call it a flash flood. But this obviously is something which is you can tie it to the location. I mean, 6 hours at certain areas would be too much. Maybe within a couple of hours we can expect that there is a kind of flood that is coming if there is a certain causative event. Flash floods are usually characterized by a very rapid rise in water, again because these are hilly areas or the areas which are called as the head catchments, or the catchments which initiate the flood situation. So they have very higher velocity and they bring along with themselves a large amount of debris. These are few pictures of the flash flooding. Flash flooding can even occur in the urban areas where let's say infiltration capacity is very less, and if there is a high intensity of rainfall occurring for just a couple of hours, and within hours this precipitation is changing into the flood, and because obviously the drains in urban areas would have certain capacity. If that capacity is exceeded, then all the water would be showing up on our roads and in our streets. In case of flash floods, the damages, if it is in urban area, the damages are usually quite severe because important infrastructure are affected by it, and also the force of flash flood is usually very high. You see, just a velocity of 9 feet per second can move a large rock, and if you exceed it to 30 feet per second, then it can even move large boulders weighing around 250 tons. So the force that is coming with the flash floods or with the higher velocities is quite a lot. Another kind of flooding that we can expect are the dam or levee failure. They again have very significant losses associated with them, and the problem with them is that you usually have a very less time to react for them, because let's say if a dam is failing in its structure or a certain embankment is failing, then you do not have a lot of time to react. The lead time for reaction would be very less, and that's why the losses are usually are high. There can be multiple reasons why these embankments or these dams or other structures fail. It's not a topic at this point, but some of them are poor decisions during the design or construction, or mismanagement in terms of its maintenance, And it can also occur because of the earthquakes. Maybe you have certain activity, or let's say some earthquake that is coming up, and it has um, um, put some cracks in your structures, which ultimately resulted in its destruction. So we are not looking into the reasons why these dams or levees or embankment fail, but we just want to look into it, that this is also one kind of flooding that we should be considering. Urban flooding we basically looked into. Then there are also ground failures, mud flows and liquefations that usually occur. Not in our areas, it's not very common, but liquefaction in other areas in European countries is quite frequent. Um, and because of them, there is also flood situation that are creating on a lower scale, on a very smaller scale. It's not in terms of spatial area, these are not very big scale events, but still these things can happen. Okay, the next is then the frequency and duration analysis. We have to turn to the Excel sheet for that. And we look at a certain data. For example, let's say this is the data that we have for different years. You have certain discharge values in cubic feet per second from 1946 to, let's say, 1975. You have almost 30 years of yearly maximum discharge that is occurring. So data is annual maximum discharge or peak discharge. So basically in 1945 the maximum discharge that occurred at a certain location in a certain river is 1810. In 1946 it was 791, and so on and so forth. So these are maximum values that occurred in 1 year. Important thing, or let's say you should always keep in mind that the first thing that you should always do when you have a data is to plot a time series graph. Just go to the time series line and try to look at the data, how the data looks like. So let's say we are just plotting just to look at how the data looks like. On x-axis you have all the years, on y-axis you have discharge values. It's irrelevant what kind of units they are, but can be cubic feet per second, cubic meters per second. This is just the overall behavior of this river in terms of its maximum discharge in different years. One thing that you should always look into is that if there are any abrupt changes that are occurring, or if there is visually, if you can see or you can detect something immediately from the time series. You see, we also we kind of see that in this period the flood levels were not that high, and in this time period the flood levels, when they were occurring, had higher peaks. So almost this is 1960 and 1964 and then 1970. So at least in this time period, on a scale of, let's say, in a gap of 4 years, whenever the flood was occurring, it was quite high flood that occurred in this location. And before this period, or let's say before 1960, all the flood values were kind of smaller, below 2000 cubic feet per second. All the values after it, whenever the flood was occurring, had a higher values. These are also the flood values, and these are also the maximum values, yearly maximum value, but these values are then smaller values. So this is the first thing that you should usually look into. Another thing that you should look into is to look at the histograms, or the frequencies of data. Now this data can be anything. I mean, I'm just looking at the yearly data here from 1945 to 1975, but it can be daily data, right? It can be daily discharge value that you can be looking at, and regardless of what kind of data do you have, the method obviously is the same. You just look at the data, and then you try to plot the histogram or the frequency of the data. The simple way of doing it would be that we go to the data tab in the Excel sheet, and then we go to the data analysis, add in, which is usually available in Excel, and then there are different tools that are available to you, and currently we are interested only in the histogram, so we just select histogram here, and we select OK. But before that I have to insert certain values. Let me just calculate what the average value here is. What is the average maximum discharge that is occurring in these 30-31 years? So I'll just write average, and then the average of all these yearly maximum values, just to have an idea how the values are. So it's almost 1600 cubic feet per second, and this is the average maximum yearly discharge. It would also be good to look at the minimum value and the maximum value that is occurring here. So minimum of all these numbers. This is a comparatively smaller data set, so you can, even by observing, you can say what is the minimum value. So I see here in all of I can immediately see 707 cubic feet per second is the minimum value that occurred in these 30 years. But when you have 20-30 years of daily data, then obviously it is difficult to do it by just observing, so you have to use these small helpful function. Also, we need to look at the maximum value that is here in these numbers, which seems to be some 5,200. So yeah, 5,200 cubic feet per second is the maximum value in this time series. Now, another important thing is that you would have used frequencies and histograms in your probability lecture, probability and statistics lecture, I think, that you attended in your third or fourth semester. But still, just a very small remark here, that for these you need to have a bin size. We need to find out that for a certain range of values, for example, let's say from 500 to 1000 cubic feet per second, how many times in this recorded time series we have value which is between these two ranges, between, let's say, 500 cubic feet per second and 1000 cubic feet per second. So how many times did the average on the yearly maximum discharge value was between these limits? This is basically what histogram tell us. So we need to have the bin range fixed, so that we can tell Excel to draw a histogram for us for that particular bin. So let's say, because my minimum value is 700, maximum value is 5,200, so let me start from 500, and then 1000, 1500, maybe now 3000, 4000, and let's say 10,000. Fine. This is my bin size, and I'd like Excel to tell me that how many times between all these values that I have, how many times there were values between 500 and 1000, how many times I had a value which was between 1000 and 1500 cubic feet per second, and so on and so forth. So this would be bin that would I would be giving to Excel to calculate or to use in calculating the histogram. So again, we go to the data tab, and then in data tab we have data analysis toolkit, and this toolkit contains one tool which is called histogram. We just select it, and then we have to give the value. So input range is your input values. These are my input values. I just select all the input values here, and then it asks for bin range, and bin range, as I said earlier, we have decided here that this should be our bin range, so I fixed that here. And then I need certain things, so cumulative percentage and maybe the sorted histogram and all those kind of things. So we have different kinds of options available to us. You can explore these options when you are having this Excel sheet, and by just clicking it we'll get the data. So you see, this is the bin that we gave to Excel, and it calculated for us the frequency, that from 0 to 500 there are no values. Fine, and it is true because our minimum value is 700, so between 0 and 500 there are no values at all. Then between 500 and 1000 there are 10 values, and similarly between 1000 and 1500 we have 10 values, so on and so forth. Between 4000 and 10,000 I have then just one value. The Excel would also give you the histogram in terms of the chart, so very clearly you would be looking at the frequency. So these are now my frequencies. From 0 to 1000 I have 10 values, and then 1500 those values. So clearly I can have this idea that how the frequency of my data is. So this was very briefly about how to calculate the frequencies in Excel. Another important thing that we need to calculate is the non-exceedance probabilities. This is very important because it tells you what is the probability of a certain value being exceeded in terms of the flood. This is also called, calculating this thing is also called the probability plotting positions. It's very easy to calculate. What you have to do is that you have to get all of your data. So you just take all this data and you copy it from that place, you paste it here, and you order it in ascending order. Fine. We are not bothering about which year this data occurred, so I'm just, for example, let's say I'm just copying this data, I'm pasting it here, for example, and then using the sort function I am sorting it in ascending order. So this would be my smallest value would be on top, largest value would be on bottom. Fine. And then to the left hand side I just write the ranks of it. So 1, 2, 3, 4, 5, 6, 7. So it will give me fill series. So it will give me that this is the first value, the second rank, the third rank in terms of ascending order. And this is the largest value which has a 31st rank. Obviously, if I copy this thing again, pasting it here, and I order it now in the descending order, then this is the rank 1, this is rank 2 and rank 3. So depending upon what we are going to do, the rank would tell us its position in terms comparing it with all the other values. So 5200 cubic feet per second has the first rank when we are looking at the highest discharges, for example, and if we are looking just at the smallest one and then in ascending order, then 707 would be having the first rank. Fine. So I just deleted these values. Now this is the first step that I did, copying it from there, pasting it here, then sorting it in ascending order. Now these are different formulas available to us: the Weibull formula, the California formula, the William-Hazen formula, and the UK formula. And you will see now that there is a very small difference between each one of them. We'll plot them and then you will see the difference between them. Just look at this Weibull formula. Weibull formula is nothing but just dividing the rank of a data, so this rank, divided by the total number of values that we have. Okay, so we have total values of 31 and this is divided by 32. So Weibull formula has the rank divided by the total number of data that you have plus 1. So if I have 31 years of data, so 31 plus 1 would be 32. So I'll be dividing 1 divided by 32, 2 divided by 32, 3 divided by 32, 4 divided by 32. Fine. And this basically gives us the non-exceedance probability of these discharge data. Fine. So and similarly the California, we'll plot it and then we'll see what non-exceedance mean. California formula is the same, but it is dividing it by the total number of data that we have, not data plus 1 point, but the total number of records that is available to us. Similarly, William-Hazen formula is a little modification, and so has the UK formula, and these formulas would be shared with you on the LMS through the PDF copies of the book that I mentioned earlier. But let us first look at what these values tell us. So I just simply plot these values again. So on our x-axis I have the discharge values, and on y-axis I have the probability values. Now what does this data tell us? Just look into it and see what it signifies. You see, for every discharge value we have a certain probability associated with it, and because we sorted our data in ascending order and then calculated the ranks and then different kind of these plotting position, this gives us the non-exceedance probability of each value. That what is the probability that the value of 2000 cubic feet per second is not exceeded for this river? Very easy would be that I look at the maximum value. So there is almost 100% chance that this value would not be exceeded in my record. Or for example, for this particular river, 5000 cubic feet per second would not be exceeded, and this is almost 100% surety level there, or 100% probability. Similarly, if I look at now the smaller value for, let's say, 1500 cubic feet per second, then I have 60% chance or 65% chance that this value would not be exceeded. So this gives us the known exceedance of the values. On the other hand, if I plot it differently, or sorry, if I sort them differently in descending order, and then I plot the graph between the two, then it gives me the exceedance probability, which basically tells me that it is almost 80% sure, or there is a 80% probability that this 1000 cubic feet per second value would be exceeded. And as I move towards the right or towards the larger values, the probability decreases. So this is reciprocal of the known exceedance probability, and this is how we calculate different kinds of exceedance probability. These formulas would be shared with you, and you need to look into it when the data is available to you. So this was about the frequency and duration analysis. Next is reservoir and channel routing. Very important concept, and at the MS level then we have a complete lecture associated with the flow routing, or a complete subject which deals with the flood estimation and control, and there are different methods of routing, and each one of them is then looked into detail. But at this level you need to know what basically flow routing is and how flow routing is calculated. Flow routing is basically a procedure to find out the flow hydrograph at a location downstream at a certain level, at a certain river, basing on the hydrograph that is available to you at the upstream location. Fine. So basically we are trying to find out how the flood or how the flow would look like when the flow reaches maybe 50 or 60 or 100 kilometers downstream. Important in that aspect is that you have a hydrograph which is available to you at some upstream location. So at this location you have an hydrograph available to you, and then downstream when we are going into the river or going along the river, we need to find out what the hydrograph would be looking like in terms of its hydrograph. And this basically is the flow routing. We already know that when we move downstream, the hydrograph would attenuate and it would also get delayed. The peak would be delayed by a certain time, so this hydrograph most probably would be associated with the location which is the most upstream. So very quick increase and then a quick recession curve. And then as I move downstream, the hydrograph would attenuate and its peak would also get lower and lower as I move downstream the river. And this is what we need to know. If I have this hydrograph, then I need to find out how this hydrograph would be at some location downstream. And this is important because we need to have these values to plan our activities associated with water and water management. So basically, as I said earlier, this helps in accounting for storages and also to look at the flood peaks, how the flood peak would change as the flood move downstream. So it has a lot of practical applications. As I said earlier, routing is basically simulating the movement of water through a channel. And there are basically two methods or two types of routing. One is called hydrologic routing, another one is called the hydraulic routing. Both of these methods use continuity equation for its calculation plus some additional information that we will be looking at. Okay, the important equations would be the continuity equation and also the Saint-Venant equation if we are using hydraulic routing. As we said earlier, there are two methods: hydrologic routing, which just only use the continuity equation, plus another storage equation, storage elevation equation that I'll be explaining in a couple of slides. And then there is hydraulic routing, which in addition to continuity also use the momentum equation. The difference between the two is that in hydrologic routing, we are calculating the flow as a function of time only. So with respect to time, we would be saying that okay, the flow at this time is this much, and the flow at another time is that much at one particular location. So let's say you are standing at point A, you have a hydrograph, and using hydrologic routing you can say that in 3 hour times the hydrograph would look like this at this particular location. The two equations, or let's say the two important inputs that we need to have in order to calculate hydrologic routing is continuity equation. This has to be available, and also the flow storage relationship. So we'll see how this flow storage relationship is used. Another one is hydraulic routing. This is also called distributed routing, and in addition to continuity equation, it also uses momentum equation. And what it calculates in addition to hydrologic routing is that it gives us flow both as a function of space and a function of time throughout a certain river stream or throughout the system. So once we apply hydraulic routing, we would be able to say that at this particular time the hydrograph was this, and then in a couple of hours the hydrograph would be looking like this, and then in addition to that we can also predict the hydrograph at some other location downstream the river. So at different locations and at different time we can calculate the hydrograph. So this is the basic difference between the two. Hydrologic routing is for particular space or particular location with different times. Hydraulic routing is at different locations. At different times we will be able to calculate the hydrographs. No matter what kind of routing technique we use, we would be having a hydrograph at one location. So let's say the inflows. Hydrograph is basically the inflow. Yeah, hydrographs, we said that x-axis has time, y-axis has the discharge value. So this would be our inflow. So inflow would be known, and also you would be having certain characteristics known to you. Those characteristics can be the stage discharge relationships or the outflow relationship with the storage. So these some kind of characteristics would be known to you. What would be required would be a hydrograph at another location, and that would be termed as the outflow. And the reach can be a reservoir or a small river stream or something like this. So basically this is our inflow, and this is our outflow after a particular time, and this is what we would be trying to predict based on the information that we have been given in terms of inflow. This equation is basically the continuity equation. Change in storage with respect to time is equal to inflow minus outflow. Fine, we have looked into it so many times, so no need to look into it now. So change in storage is basically the difference between inflow and outflow, and this continuity equation would be used in our formulas. Another equation that we said, that in addition to continuity equation, we might also need some characteristics um, of the reach, or the characteristic of river, and that characteristic can be a relationship between storage and outflow, or storage or inflow. So this relationship has to be available to us. So we have to have the inflow, and then we have to have a storage discharge relationship, a storage outflow relationship. So any relationship should be available to us in order to calculate the outflow. Now an example can be can be this equation. So for example, let's say there is inflow into a reservoir, and that inflow has or that reservoir has a weir as an outlet structure. Then if you have the outlet equation with you, because we know what is the discharge formula over the weir, so that discharge formula would be our additional equation that we would be using in predicting the outflows. Okay, in this lecture we are looking at the level pool method. Hydrologic routing, for example, has these different kind of methods available: level pool method, Muskingum method, and then some mixture of the top two. Level pool method is basically also called modified pulse model, where the storage is a non-linear function of discharge. Muskingum method assumes that the storage has a linear relationship with inflow and discharge, but we are only looking at the level pool method. Muskingum method is very easy method. There are certain formulas that we just have to put values in, and then we will be getting the outflows. This would be an assignment for you, the Muskingum method, to look into. So we'll be solving one problem now, and you can solve the same method with Muskingum method, and that would be your assignment for this week. This is modified pulse method is the most frequently used method for routing. It is also called the storage indication method. And the important consideration in this is the storage and the discharge relationship. You see, when I'm looking at this graph, you see we have two sets of graphs. One is for invariable relationship, another is for variable relationship. What it basically says is that if this is my inflow, for example, then the outflow is something like this. Now, why we call this invariable relationship? We call it invariable relationship because no matter where we move in on this graph, there would always be, for a particular storage, there would always be a particular outflow or a discharge associated with it. In other words, the level or the surface of my reservoir is horizontal, and any change in the reservoir is bringing a change in the outflow which is consistent throughout the time period. Let's say you have a very big reservoir, and that reservoir has a horizontal surface behind the embankment, or the reservoir or the water that is being collected in that reservoir has a horizontal surface, and for every 2 feet reduction in the surface or in the depth, there is always a particular discharge associated with it. Now this kind of relationship, or this invariable relationship, is usually characterized by very deep and wide reservoirs compared to the length of reservoir. If the reservoir has a very deep has higher depth, and the surface area is very wide as compared to the length of the reservoir, then this invariable relationship is usually active. The water velocity in those reservoirs is slow, and there is this single relationship between the two values. Now R is the maximum storage. This R shows the maximum storage value, and P shows the maximum outflow. So the maximum storage occurs when it coincides the inflow hydrograph, and this relationship is invariable relationship. Whenever there is decrease in the water surface, the outflow associated with it would be constant, or within certain particular numbers. On the other hand, we have this variable relationship. Variable relationship is usually associated when you have a very long reservoir which is narrow and has less depth, and the surface, the water surface is not horizontal but it is kind of inclined, which basically means that at certain location, if there is decrease in depth of 1 meter, then the discharge or the outflow would be maybe 10 cusics. But in another location, if the discharge, or let's say the level, is decreasing at the same with the same values, then the discharge is something else. In other words, to make it clear, that for every 2 meters reduction in the water surface, the discharge is something else. So for the first 2 meter reduction in the water surface, the outflow can be 500, and then for the next 2 meter reduction, the outflow can be 1000. Fine. So you do not have a particular relationship between the decrease in the depth and the outflow. In the initial case, for every 2 meter reduction in water surface, you always have a particular outflow associated with it. But in this case, even if the reduction is the same, for example 2 meters occurring at one time, 2 meters other time, but the outflow would be different. And that's why the variable relationship is something like this, where it is moving when you are when the storage is increasing, then the discharge is something else, but when the storage is decreasing, then the discharge is something else. So the variable relationship is signified. Okay, so let's look at the formula, or let's move to the final equation that ultimately would be used in level pool routing. You can go through the slides when the slides are available to you, and also to the text, but this is the important equation that ultimately we would be using. So storage, S is storage, discharge is Q, I is inflows, and J's are the time steps. So this basically is that the storage at time interval plus 1. So in the second time step, so for example, let's say this is day 1, and then storage at day 1 plus 1, so the second day storage. Similarly, discharge on the second day, and then inflow on the second day, inflow on the first day, inflow on the storage on the first day. And this equation is basically coming from this one, that storage from the next day minus the present day, or let's say now this is change in storage between the 2 days, is equal to the average inflow minus the average outflow. Fine. So J is basically the time step, and S is storage, I is the inflow, and Q is the outflow. What we will be given would be the inflow hydrograph, that for example, let's say there is a certain reservoir, and in that reservoir certain amount of water is coming, or the inflow is coming with respect to time, so inflow hydrograph would be known. And also the discharge and height relationship of that reservoir would also be given to us. What we would be doing is that we first would be developing a relationship between discharge and this value, which is Q plus 2S by delta T. This would be clear when we would be using now when we would be solving the numerical. And this relationship would be drawn or plotted, and then this relationship would be used afterwards when we calculate the other values. The next step would be to compute the discharge plus 2 into storage divided by the delta T, and now this delta T would be given to us. It can be 1 hour or 2 hour, using the equation that was shown earlier, or this equation. So for example, let's say this is the situation. These values are given to us, the inflow. So after every 10 minutes, the time delta T is 10 minutes. So after every 10 minutes, an inflow is known to us, 0, 60, 120, 180. So this is our time on x-axis, and y-axis has the inflow in cubic feet per second. So this is our inflow hydrograph, which is given to us. We have been also provided with a stage discharge relationship. So for each discharge value, what is the elevation in the reservoir? This relationship is also known to us. This is also given to us, that if my elevation in the reservoir is 4.5 feet, then the discharge associated with it would be 117 cubic feet per second. Fine. So these two relationships are known. We are also aware of the area of reservoir, which is 1 acre, and also the diameter of the outlet structure, which is 5 feet. So for example, let's say you have been given that there is a pipe which has a 5 feet diameter, and the outflow is occurring from that. So these things are known to us. Now, what are we going to do? The first step is that we develop the discharge versus Q plus 2S by delta T relationship, using the Q by H relationship which is given to us. So you see, these values are given to us. The elevation associated with it, the discharge is also given to us. Fine. This thing is known to us. Now, if this thing is known, then I can calculate the storage. And how can I calculate the storage? I can simply calculate the storage multiplying the area with the height. So height is coming with me from this first column, this one, and the area is given in the question, which is equal to 1 acre. So for every change in elevation, I'll multiply 1 acre with this elevation, and I'll get the storage. So for example, if I convert acres into square feet, then I get this value, and height is given to me 0.5. So 0.5 multiplied by the area is 1 acre. 1 acre converted into square feet is this, so I'll get 21,780 cubic feet. Fine. So I'll get this value. The first row all are 0, 0 elevation, 0 discharge, so storage would also be 0, and 2s by delta T plus Q would also be 0. In the second step, when elevation is 0.5, the discharge is 3, this is given to us, and for this discharge, if I calculate the storage area, or sorry, the storage in cubic feet, then I simply multiply this 1 acre converted into square feet multiplied by 0.5, and I'll get the storage. Once I have this storage value, then I can put it in this equation, 2 into storage divided by delta T. Delta T is given to us, which was, this is delta T, 10 minutes. 10 minutes multiplied by 60 to convert it into seconds, plus 3. This discharge is given here, 3. So I get 75.6 cubic feet per second. This value, 2s by delta T plus Q. Fine. This is important because this is the value which is coming from this equation, 2s by delta T plus Q. So we need to have this relationship. Fine. So similarly, we calculate for all the values. For example, I'm looking at this 7. So when the elevation is 7 feet, the discharge is 0.205. This is given to me already. I simply multiply the 43560 multiplied by 7 here. I'll get the value in cubic feet, which would be this one, and then I use this storage in this equation, and I'll get the 2s by delta T plus Q, which would be 122.1.4 cubic feet per second. And I simply plot a graph between the two values. On the x-axis, I have these values, 2s by delta T plus Q, all these values, the fourth column, and on y-axis I have the discharge, which is the second column here. Fine, so I have a relationship. Now what do I have? I have this inflow hydrograph, and based on this given Q by H relationship, I developed this relationship, which is now also available to me. And now I move to the important thing. An important thing is this graph or this table. This is what we will be calculating, and this is important to understand. First of all, most of the time we'll be trying to have this kind of table where you have the time index, so simple serial numbers, then the time in minutes, which is given to us, 0, 10, 20, 30, these are given to us. The inflows are also given to us, and then I'm moving forward. And how do I move forward? The first row is 0 initially, because in question it is given that the reservoir is empty. We are starting from empty situation. After 10 minutes, the inflow is 60 cubic feet per second, which gives us that the fourth column, which is the addition of the two inflows. So this is j plus 1, and this is at j, so 0 plus 60 is 60. Fine. Now I'll now move to this sixth column. Instead of the fifth column, I'll move to the sixth column, and this column give me this. Basically the formula is written here, which is 2s divided by delta T plus Q. So this 60 plus the previous value, or let's say which was in the first row, it was 0, so 60 plus 0 will give me the 60 value here. And now once I get this 60, from this I'll go back to the graph that I calculated here, this one, and I'll see what is the value because you see this 60 is 2s by delta t plus q. So I'll see on x-axis, I'll try to locate this value, and this, for this value I'll find out what the outflow is. So again I'm coming to this graph that I developed earlier. I'm trying to locate this 60 value here on the x-axis, and I'll see what the value here is on the outflow curve. So for example, if I have 1000 value, I'll come here, I'll try to locate 1000 value, and I'll see that the outflow is 150. Now at this time I have the 2s by delta t value of 60. I'm coming to this x-axis, trying to touch the graph, and then trying to read the y-axis value, which will give me the outflow. Fine. So I'll take this value, and this would be my outflow, which is 2.4. Now once I have this outflow value, I'll use that outflow value to calculate the value for this fifth column, because you remember we left this fifth column. When we reached here, fourth column, then we jumped to the sixth column. From this column we calculate the outflow, and now we have to find out what this value is for the fifth column, and that fifth column formula is written here. So I'll simply, what I'll do is that this is 2 multiplied by outflow, so 2 multiplied by 2.4 will give me 4.8, and I'll deduct this value, this 4.8, from this 2s by delta t value, which is this one. So 60 minus, this is 60, this value here, 60 minus 2 times 2.4, and this will give me this 55.2. Fine, and this will be my fifth column values. And then I'll move to the third row. In the third row, the time again, it's 20 minutes, inflow is 120. I'll come to the fourth column. In the fourth column, I'll just add these two discharges, 60 plus 120, I'll get 180. Once I reach here, 180 plus 55.2 would give me 235. Again, you see we left the fifth column. We just went from fourth column to sixth column by adding this 180 to this 55.2. We got 235. For this 235, I'll go back to the curve that I developed earlier. This one, 235 is somewhere here, and for this I'll see what the discharge is, which is somewhere 20, around 20. Yes, so 17.1. For this I saw that I had 17.1. Then I use this 2 multiplied by 17.1 minus 235 will give me 201, which will be the fifth column. And in this way I'll complete the whole table, and ultimately I'll be having this outflow curve. So this inflow was given to me, and this outflow is now known to me. I'll plot these two things. So this was the inflow, and now this is my outflow. So we basically routed the flow from the reservoir to at the same location when there was a 5 feet of, let's say, a pipe with me, and the outflow was calculated. So this is how the routing is performed. I'll upload all the information on the LMS, and then you can go through the text to understand the thing. If you have any questions, please put them on LMS, and I'll try to answer them as quickly as possible. Thank you, and Allah Hafiz.